Good afternoon, everybody. We're here to talk about a year of democratizing machine learning with Kubernetes and Kubeflow. My name is Fei, and I'm a customer engineer at Google.
I'm Dave Aronchick. I'm product manager and co-founder of the Kubeflow project. I guess this is it. Okay. So with that, this is a really auspicious occasion. This is the first, obviously, KubeCon in China. This is my first talk in China. I've been representing Kubernetes since January of 2015, and this is really, really exciting. I can't tell you how many people have come up to me asking to have talks in China about Kubernetes and Kubeflow and ML. And so I hope I do you all proud, but I'm very, very excited about this. Excuse me. So, we kind of gave away in the talk, but, a year ago, we started the Kubeflow project. And the idea was that we had heard all the time this question: what is machine learning? And it's really a hard question. So many people have so many different takes on it. Is it something just incredibly basic, like advanced linear regression? Is it something that's going to take over the world? Who knows? But the reality is that at Google and across the machine learning industry, we think largely it's this. It's a way of solving problems without explicitly knowing how to create a solution, where you have data and features and sources for so many different things, and what you're really looking to do is get to an answer, yet you're not exactly sure how things correlate. And that's a really powerful thing, and we went into Kubeflow thinking this very thing. At Google, everything at Google is touched by AI in some way. And one of the most profound ways is this example that we have here with Google data center operations. Obviously data centers are one of our most expensive, most costly, most important things that we do. And for us, we hire great engineers who think about problems very, very deeply. When we took that knowledge, when we took all the data that we collected and we applied machine learning to it, we found out a really amazing thing, that even though these people were great, they were the best data center engineers, arguably in the world, we were able to make huge progress against them. And you can see it here. This is a way to measure data center effectiveness. It's called power usage effectiveness, where you measure the amount of power going in and the amount of computation that you get out the other side. Ideally, you want it to be as low as possible, meaning you have the lowest possible power going in, and you're getting the most powerful computation out of it. In this case, it started out very high. We simply applied ML, and that wasn't simple by any stretch, but we applied ML to the problem, instantly cut down our power usage, and then turned it off, and it came back. And we saved literally hundreds of millions of dollars doing this. And there's a great blog post on google.com that talks about all the ways that we're saving energy. And this is really important, right? It's not that our data center engineers didn't know all these elements of launching of having a data center, of how to make it efficient and all these things. They had all the data, but they just didn't know how to approach the problem, and machine learning was able to do that for them. And now, the problem is that ML is hard. Those people, those excellent data center engineers, they didn't know how to go and approach this from an ML perspective. We had to get brand new data center engineer or data scientists to get in. And the reason it's hard is because of something that Kubernetes helps to solve, which is all the steps around setup and management and declarative deployment and all these things that data scientists don't want to think about. They want to just think about models and pipelines and things like that. And the reality is that they had to think about it. And so what we wanted to do was think about changing the game with machine learning in the same way that containers and Kubernetes changed it for overall deployment, and create something called cloud native apps. Now the question is, could we get to cloud native ML? What would it even look like? For us, it looks kind of like the following. When people think about machine learning today, they really think about a single element, right? They think about building a model. Are you going to use Paddle or TensorFlow or Scikit? How quickly does it converge? What's the accuracy level, and so on. But the reality is that a machine learning pipeline looks a lot more like this, where you have lots of microservices loosely coupled together, and what you're trying to do is get to a solution that involves actual production readiness, even if you're a data scientist working at the beginning. And And this is what that data scientist experience looks like. Whereas the first one might be relative to the platform and the various services, a data scientist wants to do something completely separately. They want to just be at Jupyter level or Docker. They want to train their model. They want to deploy it. And they want to integrate it into their app as quickly as they can. And worse than that, even with that complex pipeline, I haven't even started to get to where the real problems are, which is around the entire stack end to end. You start at the model and you walk all the way down, whether or not it's UX, tooling, storage, runtimes. These are all things that you're going to have to deal with. And that entire pipeline that I was talking about, that's just the very top of it. All the other things kind of sit under the hood. And now, to make it even more complicated, it doesn't just sit under the hood in one environment. It sits under the hood in multi-cloud environments, where you now have to replicate that entire thing over and over again. In this case, 81% of enterprises have more than one cloud, and they don't just have more than one, they have up to 5, which makes your problem much, much more complicated, whereas this might be your experimentation one. You go one step further and have to replicate that at same environment for training, and then finally your same environment for cloud. So this is a very, very complicated problem. And this right here is why we introduced Kubeflow. In December of 2017 at KubeCon Austin, we introduced this portable framework that let you declaratively describe a very complicated machine learning framework, end-to-end pipeline, using the elements of Kubernetes to make your deployment and management much easier. Our mission remains the same a year in. We want to make it easy for everyone to develop, deploy, and manage portable distributed ML on Kubernetes. And what that looks like is this. You have that base layer of Kubernetes. You know that it runs the same everywhere. As Dan Cohn talked about earlier, the investments that the CNCF and Kubernetes projects make in conformance means that you know, no matter where you go, you're going to be able to plug into a rich Kubernetes deployment that has a minimum bar for the APIs and other objects available. And then on the left, you describe your pipeline using Kubeflow. And Kubeflow is something that you can stamp out in each one of those locations in a declarative way, knowing that because you have Kubernetes to base it on, you're going to be able to replicate that very quickly. And what that means is we now do have cloud native ML. We have a portable framework which operates at the cloud level, loosely coupled together, microservice oriented. In the years since we've launched, we have a tremendous amount of momentum. 1,900 commits, over 100 community contributors, with 30 different companies contributing, including the list you see here, and many more. And when I say what it means to have a rich community, it looks like the following. When you think about one of the most successful communities in the world, Kubernetes, it looks something like this. And I know that it's a lot of different companies contributing in a lot of different ways. Let me kind of simplify it for you. It looks like this. That's Google, and this is not Google. And that's really important, right? We at Google are not the #1 contributors. Everyone else is. That is so important. And it took us years to get here. You know, the first year, second year, we were over 50%. That was incredibly important for us to get to that point where other people could find the place in the ecosystem to make it their own. For Kubeflow, it looks like this. Here's different companies contributing. And to simplify it again, Google and not Google. And we're already over 50% of our contributions come from non-Google. This is what healthy community looks like. And let me take it one step further. Folks just aren't working on bugs. And I'm not saying bugs aren't incredibly important. They are. We know we want to get to stability. But the reality is, it's really significant contributions that move our platform forward very, very quickly. For example, we have a great framework in the core of the platform called Katib. It helps do hyperparameter optimization. It's plugged in. And in particular, something Fei will show in just a minute, we make it very, very easy to do this even with very little code. And that came from NTT, and we couldn't have been happier about it. Second, we have a brand new serving framework, which literally just launched 2 months ago, I believe it is at this point, from NVIDIA. It's called TensorRT, and it makes serving on GPUs much, much more efficient, including multiple models per GPU, per node, heterogeneous GPUs, and environments. And it integrates with the underlying autoscalers and latency and health metrics. Again, external company contributing to the core of Kubeflow. This is incredibly important. One more example is Argo. from Intuit. I mentioned that Argo's already in the box. This is an incredibly powerful system for workflow and orchestration and pipelines. We'll touch on that. And it really allows for doing Git ops, you might have heard, for launching it. For declaratively rolling out your machine learning pipeline. So that's everything. Now I'd like to hand off to Fei to talk about Kubeflow 0.3, which we're happy to announce.
Quicker.
Yeah. Sorry.
So we recently released Kubeflow 0.3. And in 0.3, there are two major themes that we really invested a lot in. So one is around how to make Kubeflow easier to deploy so you can have a much better getting to started experience. The other part we want to make investment in was how to make the development experience on Kubeflow more powerful and able to use in different use cases. So on the deployment side, we released a new deployment CLI called a kfcontrol.sh. It's a bash script where you can use to install all the Kubeflow components just from one command. I'm going to show more of that later as well. The second thing for deployment is that we're having a much simpler setup. And later, I'm going to show a one-click to deploy of how you can provision the infrastructure as well as install all the Kubeflow deployment with just one simple click. On the development side, we are also making a lot of different investment. And I just want to highlight two of them. One is our PyTorch operator. When we first got started, we focused on TF job. And now we're listening to the community, and we're hearing that people care about using PyTorch on Kubeflow. And now our PyTorch operator has feature parity with TF job. One of the biggest obstacles to getting quality models is to make sure that you have the proper hyperparameters for your models. And that's why hyperparameter tuning is super important to us. And as part of Kubeflow 0.3, we announced a hyperparameter tuning CRD. It's called Study Job. That enables you to do hyperparameter tuning and searching without needing to write any code. So I talked about the general themes of what we have in Kubeflow 0.3. Let's double click on some of the things, and I'll show a couple demos. So the first one is for deploy. We have something called click to deploy. We've been hearing from the community that it's very difficult to get started with Kubeflow because you need to install packaging libraries, and then you need to download and install the different components that comes with Kubeflow. We want to make that getting started experience much easier. So what we came up with is a one-click installation tool. It is available to you with a very clean web interface, so it's a web app. And the way you would use it is basically it uses a Bootstrap container, and there's this one bash script that you can use, and it has all the necessary dependencies included. With the bash script, you can then use it in any infrastructure deployment tool. So that would be a deployment manager on GCP or CloudFormation on AWS. And finally, what we're going to see now has no template tool needed at all. It's really just one click to deploy and also provision all the infrastructure that you need for Kubeflow. So let's take a look at what it means. So what you're seeing now is our Kubeflow click to deploy interface on GCP. All you need to do is specify which project you want to deploy in, the name of the deployment, and some security configurations. Then the click to deploy will actually provision the infrastructure on top of GCP, meaning that there will actually be a cluster that's spinning up that will host your Kubeflow components. So as you can see, after I did the click to deploy, now I have a Kubeflow cluster. It's provisioned through the click to deploy on GCP. When I go to the workloads page and I refresh to see what actually happened on the cluster, you can see all the deployment and pod that comes out of the box for Kubeflow. And this, remember, all what you just seen is one click to deploy, so you're not using any templating tool like KSonnet. The second thing that we want to highlight is Kubeflow pipelines. This was announced very recently. And what we see and notice in the community is that machine learning solutions are often multi-staged. There are a lot of components currently in Kubeflow that deals with each of the stage, but it was very difficult to put all the different stage and components together. And that's why we have Kubeflow pipelines. It is a microservice platform. It is designed to enable reusable components and workflow orchestration. So it is a one place where you can orchestrate all the different components and run machine learning end to end. What it is that it's a Python SDK, and you can use the Python SDK to describe and containerize your machine learning task. We choose Python because this is very natural to data scientists, so we can really meet where they are, so that they can themselves describe what they're trying to do with their whole machine learning task. After they describe their pipeline in the Python SDK, we will compile it to Argo, which is coming already in the box from Kubeflow. And we also, as pipelines, we offer a front-end GUI to do experiment logging as well as analytics. What's really important about this is that all of these steps are containerized. What that means is that the data scientists will be able to compose what they're trying to do to their needs to form the pipeline they're looking for. Let me show you how that looks like in action. So let's start by looking at a very simple pipeline. So in this pipeline, we will use a very simple training example that utilizes GPUs. So in this Python script, as you can see, we have two main operators. The first operator is the training operator, and the second operator is the post-processing operator. In the training operator, because this is all container-based, we're getting an image. This is where our image is. It's a very simple, straightforward MINS example, and we are using GPU to train it. As each step of pipelines, it has a series of inputs parameters as well as output. So for example, in this training container, it has 3 inputs that we're giving it. So the first one is learning rate. Second one is number of layers, so basically how many layers you have in your neural network. And the third one is what kind of optimizer you're choosing. So that constructs a single operator. The second operator is the post-processing. It's just like a vanilla post-processing step. And here is where we're actually chaining those two together. So the first training step, we put in our input parameters, and then we chain the output from this step to the post-processing operator so that we actually forms a DAG. And after you have chained everything in your graph, you then compile your Python script. It will actually form a YAML file. So the second step, I will actually compile my Python script. Here is the YAML file that it generated. So as I mentioned, the whole point is that we want to meet data scientists where they are. And in this case, it's actually Python. And from the Python, we generate the YAML file, and that can be consumed actually by Kubeflow and Kubernetes. As you can see, the YAML file generated is quite long. So here, what you see here is the actual pipeline GUI. It comes out of the box today with Kubeflow. On the left side, you can see that we offer pipelines experiments. And on the right side, it comes out of the box with a series of sample pipelines that you can explore into. So let's click into one of those sample pipelines and look at what it looks like. So in this sample file, each step in the graph in the DAG is a containerized step. And this one goes all the way from validation to pre-processing to training and to prediction. As I mentioned, each step is a containerized step. It has a series of inputs and series of output. The graph really makes it easy to show the data scientists what the steps are, what the inputs are, and how they're connected to each other. Okay, after we saw the sample steps, let's take what we just saw, the Python file and the YAML that it compiled. We can upload the YAML file into the pipelines UI. And now you have a new pipeline that's on the GUI. So we have the concepts of experiment and runs. Because the goal of the pipelines is to make sure that you can reuse your component as much as possible. So each experiment can have multiple runs, each with different input parameters. Here you can see those are the 3 parameters that we specified for the training step. What you can do now is actually to start an experiment, meaning that you will run it one time. So let's say we run it for the first time. The name will be pipeline run 1, and here are the parameters that we put in. So right here, you can also track where your experiments are and see some of the parameters. So those are the things that I want to show you for pipelines. Let's go to the next components that we want to highlight. So we want to talk about autoscaling. And the reason we want to talk about it is that today, if you want a data scientist in an organization wants to have something, after they have a model working, and when they want to train things in scale, they have to talk to somebody else in the organization, the IT ops person. So our data scientists say, my model is working great, but I need 6 nodes. The IT ops person is there to help, but she's really pretty busy. So it's going to take some time for this to actually happen. In the meantime, data scientist kind of is blocked on what's going on. So when the IT ops person gets to it, she provisions 6 nodes. The data scientist is happy and continues to do her work. And after doing lots of work, all the training is done. She is kind of wanting to move on to other things to finish her job. In the meantime, it's very likely that the both people forgets to turn off the nodes that provision. And that's really bad because a lot of these cases, these involve GPUs and it's going to cost lots of money. So that's why we have integrated jobs with auto-scaling feature. So our goal is that the data scientist just needs to describe the job. Kubernetes will take care of the rest. So that includes the CPUs they're looking for, the memory, as well as any accelerator that's needed. So be it GPU, CPU, FPGA, TPU, what have you. When the job is done, the resources themselves are going to be automatically deleted. So things will scale down by themselves. And these resources, you can also have a maximum scaled parameters. So your data scientist wouldn't be asking for like 10,000 GPUs all the time. So in this scenario, what will happen is that your data scientists have their model ready. She wants to train things at scale. She then writes a file to specify what resources she's really looking for. So in this case, she wants 6 replicas. The GPUs are provisioned automatically with Kubeflow and Kubernetes. When the job is done, the resources are gone automatically. So they don't need to worry about over-provisioning or overspending or resources sitting idle. And our IT ops people, she will be happy because now she has free cycles to do things that matter, or maybe talk about YouTube. So let me show you what that looks like in practice. So this is going to continue what we were just looking at in pipelines. So remember, when we first provisioned our GKE cluster, we only had 1 node pool, and that node pool is CPU only. But the training step in my pipeline actually requires a GPU. So what's going to happen there? When we look at the workloads, we see our pipeline is currently initially unscheduled. And when we go there, we can actually see the reason behind it is that there is not enough GPUs that's required to do the training. So there is a feature called node auto-provisioning that's able to detect the reason why the job is not being able to schedule. And now it is working to spin up a new node pool that's able to accommodate your job. So what you're seeing right now is that because we have the pipeline job that requires the GPU, now instead of one node pool and 3 nodes, we have 2 node pools, with the second node pool have the GPU to accommodate the pipeline. Okay, now when we refresh that, we could see that the training is done. But in this scenario, we could see that the validation accuracy is only around 10%. So that's not very ideal. Earlier, we talked about how hyperparameter tuning is super important to how data scientists do their work. And now I'm going to show you how this will work in the Kubeflow scenario. So in Kubeflow 0.3, we announced study job, which is the CRD for hyperparameter tuning. What you can do here is that you want to have a hyperparameter tuning job to make sure that we have the right input parameters for your training job. And here I apply the YAML file. You can see that this is our study job spinning up. And we could have a quick look at what that study job looks like. So this would be how I describe my hyperparameter tuning. In this case, you can see that I'm actually trying to tune 3 different things. The first thing I'm trying to tune is the learning rate. The second thing is the number of neural network layers. And the third thing is what kind of optimizer I'm looking for. And again, we want the hyperparameter tuning job to use GPU as well to maximize performance. Again, you can see that in the beginning, there was not enough GPUs because we're looking for more GPUs for hyperparameter tuning. But eventually, it spins up 2 more GPU nodes to accommodate this job as well. As part of Katib, our hyperparameter tuning component, it comes with its own component called ModelDB. So this is a front-end UI that shows, that help you visualize and analyze the results of your hyperparameter tuning jobs. So in this example, you can see on top, so the y-axis is the validation accuracy, and each of these dots represent a new run of job we're trying to see. So you can see that some of the runs have very low accuracy, around 10%, and some of them have higher accuracy, around 99%. So naturally, you want to be able to analyze why you have such a difference. And ModelDB will help you do that. So the first thing we try to do is we try to do a group by on the different optimizers, and we want to see their average validation accuracy. So as I mentioned, we're looking at 3 different optimizers, and from this graph, we could tell immediately that one optimizer was the trouble. So we could either select the atom operator or the SGD operator. And furthermore, we want to do a little more drill down. So let's say we only filter on the runs that uses SGD as the optimizer. And then from the ModelDB UI, you'll be able to group by on the different metrics. So this time, let's say group by a number of layers. And in this case, you can see it's either 2 layers or 3 layers. It doesn't really make a difference to your accuracy, so that doesn't matter. And then have a look at learning rate, and similar things apply. So after we have the insight into our hyperparameters, we can go into our pipeline and then do a second run. This time we know what to put in for the optimizers. So instead of the previous one, we will put stochastic gradient descent, because we know that's the one that's going to give the best result. Now we run the pipeline for the second time. Go back to the graph. You can see that the training job is running at the moment. And this time, we were able to achieve more than 99% of validation accuracy. And again, because this is a DAG runner, we're able to do the post-processing immediately after the training. And what's most important is that you could see now, we used to have 6 nodes, 2 node pools, with 3 different GPUs. But after we run our 2 pipelines, as well as a hyperparameter job tuning job, we're back to 3 nodes. This is exactly where we started. Instead of having to manually tune down or spin down your nodes that has a lot of resources attached to it, we ended up spinning it down automatically for you. So you don't really have to worry about any of that. The auto-scaling really comes to the rescue. So that concludes my demo. I'm going to hand it back to David to talk about roadmap.
So thank you so much, Fei. We are just getting started. We are quickly marching towards 1.0 and would love to hear your feedback. What are the things that are missing? What are critical, particularly around enterprise requirements, things like upgrades, integration with IAM and RBAC. One of the things we've heard a lot about is how to be more closely tied with Jupyter. We know that Jupyter is the place where data scientists are working right now, and we want to make it very, very easy to tie those together and provide a much richer pipeline experimentation and model management. These are core things that we've already heard about. We're trying to get to them by 1.0, but we'd really love to hear what you'd like next. And I really want to stress this. It is a brand new world. The people in this room, the people watching this on the video, you have the ability to make huge changes in industry. I strongly ask you all to think deeply about ethical, sustainable ML that can help the world move forward, because we really do have a chance to make an enormous change. And we hope that things like Kubeflow will help enable that and give the power to data scientists to make that happen. Quickly, we are open, in every way it's possible to be open, community, design, open source. Come to GitHub. This is not by any stretch a Google-only project. We want to continually meet your needs so you don't have to go out and build your own bespoke platforms. And with that, off we go. Any questions? Yeah. So we are in the midst of, we already have some governance proposals right now. We hope to, I don't know, by the end of the year, have a more formal external governance proposal. That is absolutely a core goal. Any other questions? Okay. Oh, yep. So the question was, if I understood, during the hyperparameter tuning, we store the outputs of the various choices that the hyperparameter optimizer was using. We don't store the artifacts of the model. We're just doing, Katib is storing the metadata related to the model in ModelDB, and that's what's allowing the comparison. In order to do a full model run, you would then do exactly like Fei did on the board. You would take that metadata, put it back into your pipeline, and then that would do a full training run. Does that answer your question? Okay. Yeah. Last question. Yeah. Yeah. Yes. So the question was, if you're new to machine learning, should you use Kubeflow to get started? And is it feasible to use it on a single computer? The direct answer is you can certainly experiment. Jupyter and Conda and these things are great. And they're great ways to try out machine learning, and we recommend it. That said, the purpose, the design behind Kubeflow is to work great all across the spectrum, whether or not you're on a single laptop like this, all the way up to a multi-cluster deployment. And the benefit is, because you're describing your entire machine learning pipeline using very standard tools that run great anywhere, including Minikube on your laptop, it means there's very little change when you decide to graduate to larger and larger machine sizes. It'll work fine no matter where it is. Now, to be clear, on your local laptop, you're not going to want to download a petabyte of data and do a full training run. It's great for experimentation. Jupyter comes in the box. TensorFlow job comes in the box. PyTorch comes in the box. Katib comes in the box. These are all things that are very trivial, or they may not all come into the box, very trivial to install. And you can get it running even locally and see all the richness that you saw here. It is explicitly, to be clear with everyone, it is explicitly our goal to be as easy or easier than just going and doing pip install foo to get starting with machine learning. And we know we're not there yet, but with the investments that we made around KF control and other things like that, we're hoping to get there very quickly. All right. Thank you all.
Thanks, everybody.